Okay, guys, we're going to go ahead and get started. Got a packed house tonight. Must be a good speaker. All right. Thank you, everybody on Zoom and everybody in person, for coming to the 26th August general meeting of the Mount Diablo Astronomical Society. Do we have any new members in the house? All right. Thank you guys for coming. If you don't know, there are bathrooms through this doorway around to, if you need to leave at any time. We will have a break for snacks in the back. We're going to have some announcements now. And then our member, Ken Coates, he's our MDAS member and also does our outreach for us. He's going to be giving a lecture, the What's Up, Landing on the Moon is Hard. He's going to be joining us via Zoom, and he will not have a video on, but you'll be able to hear him and see his slides. And then we're going to have the break for snacks, and then our main speaker, Martin Sirk, will be discussing black holes, dark matter, and dark energy. We'll be starting about 7:45 with his presentation, and we will not have for our Zoom audience, we will not have a camera on him either, but you'll be able to hear him and see his slides, okay? So we've been really busy with star parties, outreach. We've had, lots of society nights. Just a reminder, and if you have any information, MDAS.net is where you can find the schedule, upcoming star parties. Barcroft just ended. I did that for the first time, just got back yesterday, still recovering from the altitude and lack of sleep, but it was a great time. So the last star party, CalSTARS, next month, the 17th through the 21st. Again, go to the website if you're interested. Our next outreach events are on there, and our public astronomy night in September on the 27th. So I'm gonna stop sharing now. And Ken, are you ready to go?
I am ready to go.
Okay.
Can you hear me okay?
We've gotten lots of nods, yes.
All right, so let me share my screen. All right, hopefully you can see my screen.
Yes.
Yes? Okay. All right, so I'm Ken Coates, and I'm here to give a presentation on landing on the moon is hard. So I have a lot of material, so I'll hold questions till the end, please. So here's an outline of today's talk. I'll go over the history of moon landings through the 1970s. Then I'll cover the more recent landings starting in 2013. And then private companies have started landing on the moon, so I'll talk about that. And I'll finish up talking about the future. So the early missions to the moon were designed to crash into the moon, which I wouldn't call landing. So we're going to talk about the first soft landings on the moon. And so in 1966, both the USSR and the USA successfully soft landed on the moon. The Soviet Luna 9 mission landed in February. I would call it a semi-soft landing, because just before impact, it ejected a spherical capsule that had an inflatable airbag that bounced on the surface and opened up like a flower, and then it started transmitting. It took the first images on the surface of another celestial body. It also had a radiation detector and temperature sensors. The radiation detector showed low levels of radiation on the surface, meaning that it was safe for humans to go to the moon. NASA's Surveyor 1 mission followed 4 months later. It landed just using retro rockets, so I would call that a real soft landing. It had a color television camera and transmitted over 11,000 images. On its legs, it had strain gauges to measure the strength of the lunar soil. And it was found to be similar to the soil on the Earth. That meant you could safely land something on the moon with humans in it. So that was important. It also had a temperature sensor, which measured the range of lunar temperatures. So it gets down to minus 140 degrees C at night. It was when the sun isn't up, and about 120 degrees positive C during the day. So there's quite a temperature range. Now this picture here, the top picture is the Luna 9, but the bottom picture is actual, this is actually Surveyor 3. There were more than one mission. And Apollo 12 landed very near Surveyor 3, and they actually walked over to it and retrieved the camera and other equipment to bring back to Earth to be analyzed to see how they held up. So the question is, those were 2 successes, but the question is it easy to land soft? And actually, it was pretty hard, turns out. The Soviet Union only succeeded twice out of 15 missions to land on the moon. There were 9 launch failures, 3 crashed into the moon, and 1 missed the moon altogether. The USA did better with 5 of 7 successes, but still had 2 failures. I think because of the 6 of the 7 Apollo missions were so successful, people remember those more and assume that landing on the moon was easy back in the 1960s. They forget that Apollo 11 almost ran out of fuel before landing. And of course, that was the serious failure on Apollo 13, but the astronauts returned safely to Earth. The last Apollo mission was Apollo 17 in 1972. And one thing I wanted to note here, is all this talk about going back to the moon. So far, we've only spent a total of 12 and a half days on the lunar surface, so we barely even visited there. So after Apollo 17, the Soviets tried twice more to land softly on the moon. Luna 23 crashed, but Luna 24 was successful and returned lunar soil to the Earth. After that, pretty much everyone forgot about landing on the moon and concentrated on low Earth orbit with various space stations. There were no more landing attempts till 2013. And that's when China landed their Chang'e 3 spacecraft on the near side of the moon. It included a lander and a rover called U2, which is a mythical jade rabbit in Chinese folklore. Both the lander and the rover operated for over 2 years, off and on. They both used radioisotope heating units to keep them warm during the lunar night. Remember I said it was 140 degrees below zero C. But for power, they used solar panels. The mission concentrated on lunar geology and astronomy by deploying a UV telescope. Of course, UV telescopes don't work for the surface of the Earth, so that was some new science there. China's been very successful landing on the moon with no failures. Chang'e 4 was the first spacecraft to land on the far side of the moon. It was able to communicate with Earth using a relay satellite. They put in the Lagrange 2 point on the far side of the moon. It was beyond the moon on the far side. It also deployed a rover like the first one. Chang'e 5 returned lunar samples from the near side of the moon, and Chang'e 6 returned lunar samples from the far side of the moon, the first samples from the far side of the moon. Future missions, Chang'e 7 and 8, are going to try to land at the South Pole of the moon and test in situ resource utilization, which I'll talk about more later, in anticipation of supporting a lunar base. So like I said, China's had a lot of success. How about other countries? Well, Russia tried to return, because they're not the Soviet Union anymore, they're Russia. They tried to return to the moon in August of 2023 with Luna 25, and they were trying to go to the South Pole as well. But it crashed due to a software bug in the onboard control system. And there's some speculation that they were rushing to beat the Indian lander, which was on its way there at the same time. Now, India was more successful with its first landing attempt, the Chandrayaan 3 mission. It also carried a rover like the Chinese missions and had a very successful mission operating for a full lunar day of 14 Earth days. So the lunar day is 28 days, and the daytime part of the day is 14 days, and the nighttime is also 14 days. So like India, China are like, so India, like China, is batting 1,000. They've had one successful mission and no failures. Let's talk about private companies landing on the moon. That's a lot of excitement about that lately. So it kind of got started in 2007 when Google and the X Prize Foundation announced the Google Lunar X Prize competition. It was aimed at promoting private investment in lunar exploration. It challenged privately funded teams with getting less than 10% of their funding from a government to be the first to land a robotic spacecraft on the moon, travel 500 meters across the surface with some kind of, in some method, they didn't really explain how, and transmit high definition video and images back to Earth. There were a total of 30 million in total prizes, with 20 million for the first team to do it, and lesser prizes for the subsequent successful teams. So the 5 teams listed here had verified launch contracts with a rocket company in 2017. Unfortunately, none of the teams succeeded even with the time extensions to March of 2018, so the competition was shut down. However, remember some of these teams because they're going to come up later next. They didn't stop working. So Space IL, one of the Lunar X Prize finalists, attempted to land on the moon in April of 2019. This was the first attempt by a private company. But unfortunately, it crashed due to a command error during the landing sequence. And infamously, the Space IL team put a capsule with tardigrades in it as an experiment. Those are small animals that live on the Earth. And they're known for their ability to survive in a cryptobiotic state, which is a new term for me, but I learned all about it on this researching this talk. That's where all metabolic functions cease, but they can be brought back to life with rehydration with water. Even if they survive the impact, it's unlikely they'll be rehydrated without human intervention. Maybe if a comet hits it, then maybe it'll rehydrate. I don't know. But the good question is whether this was legal to send organisms to the moon. Well, it turns out, I've talked about this in previous years, the Outer Space Treaty is the only governing law in outer space. And it prohibits countries from deploying weapons of mass destruction. Space IL is a private company, they're not a country. I'll leave it to you to decide if tardigrades are weapons of mass destruction. The second X Prize finalist, Hakuto, attempted to land in April of 2023. It crashed due to a software glitch during landing, which it miscalculated its altitude and then it ran out of fuel. And Astrobiologic Technologies launched its Peregrine lander in 2024, but a valve failure soon after launch led to a fuel leak and it never actually reached the moon. So Astrobiologics was part of the Google Lunar X Prize, but they didn't advance to be a finalist. So they were at least inspired by that. The next group of commercial missions were in response to NASA's Commercial Lunar Payload Services Program, or CLPS for short. It's a NASA program that contracts private companies to deliver scientific payloads to the moon. Intuitive Machines landed its Odysseus lander on the moon in February of 2024. It is considered the first soft landing on the moon by a private company. But I again would call it semi-soft since one of the landing legs broke and it tipped over. Its operations were curtailed because of the tipping over, but it did transmit some data for about a week before succumbing to the lunar night. Now, Firefly is another CLPS contractor, and its Blue Ghost mission was completely successful. And I'll talk about that after I go over some other attempts. So stay tuned for that. Intuitive Machines was back again in March of 2025 with its Athena lander. It landed in a crater near the south pole of the moon and again tipped over. I think it landed on a slope is what their excuse was this time. So are you seeing a pattern with Intuitive Machines? And here's a picture of their lander. And they've been criticized for having a very tall lander. But they claim it has a low center of gravity because the rocket engine at the bottom is where most of the weight is. So, but you'll see in a minute, their next lander looks a lot different than this. Now, iSpace Hakuto, again, a Lunar X Prize participant, tried again in March of 2025, but their second attempt also failed in descent to the moon and it crashed. So what's the record for commercial attempts? There have been 7 attempts starting in 2019 through May of 2025. 5 have failed, 1 partially succeeded, and 1 was a complete success. So I'll call that a 1.5 successes. That's a 21.4% success rate. Now, if you recall from the beginning of this presentation, that's actually quite a bit better than the Soviet Union did. They only had 13.3% success rate, but not as good as NASA or particularly the Chinese, which their success rate is 100%. So got some more work to do. So there are dozens of robotic missions proposed over the next 5 years, but I'll just talk about the next one that's likely to blast off. And that's again the Intuitive Machine, which has yet another CLPS contract. So this is their Griffin lander. Now, if you notice anything different about this lander compared to the other 2 that tipped over, you'll see it's a lot wider than it is tall. So, and in December of this year, it's headed for the south pole of the moon. There it is again, the south pole of the moon. And this is a flat area with the potential for resources like water ice in permanently shadowed areas. The lander will be the heaviest one since the Apollo lunar module, and has a payload of 500 kilograms. It will deploy Astrolab's Flip test rover, which is a replacement for the Viper rover, which was canceled. That mission was canceled. I think we have an upcoming speaker who's going to talk about the Viper mission, but as far as I know, that mission was canceled by NASA. And second, there's also a second smaller rover from Astrobiotic. You remember they're one of the companies that failed with the soft landing, but this points out that in the U.S., and mostly in the U.S., other countries too, Western countries, there's an ecosystem of private companies that are building space hardware. That's going to be important with going forward with attempts to get to the moon. So let's talk about human landing. So I've talked about the space race some in my other What's Up talks over the last few years. So the space race in the 1960s was between the USA and the USSR. And in the 2020s and beyond, it'll be between the USA and China. So there's a new space race coming, believe it or not. The US has the Artemis program. And I talked about that in my presentation last year about populating low Earth orbit, the moon and Mars. The current plan is to orbit the moon with 4 astronauts in 2026. Here's a picture of the crew right here. And land on the moon near the South Pole in 2027. Following that, a permanent base on the South Pole is planned for the early 2030s. This base would allow astronauts to spend weeks at a time on the moon. China has a rival plan called the International Lunar Research Station, which I also talked about in last year's presentation. They are planning to land humans on the moon in 2030 and establishing a permanent base afterwards. Do you see any possible conflict here? So just keep this in mind going forward. See what's going to be happening. It could be exciting. But we saw earlier, China has a very robust record of landing robotic spacecraft on the moon. They recently released this video, I think in the last week or two, of testing their lunar landing module. It's designed to land 2 people on the moon. So I'm going to play this video. Hopefully it'll work. This is a test rig they set up to simulate lunar gravity. It was firing its retro rockets now. As far as I know, that test was a success. They're kind of secretive, so they don't really tell us too much of what they're doing. But so the USA moon lander, let's talk about those. So NASA has contracted with SpaceX and Blue Origin for moon landers. SpaceX's version is based on the Starship spacecraft. That's the tall one on the right here. And just today, a couple hours ago, it just finished its successful 10th test mission. It was a complete success. All mission parameters were met. Of course, they've had a few failures leading up to this one, but this last test was a complete success. So that'll be in the paper tomorrow and your news sources. Blue Origin's lander is called Blue Moon. Here's a picture of it here. Their goal is to have an uncrewed test landing of a prototype on the moon in 2026. So NASA believes in getting at least 2 sources for things, which makes sense in case one has problems. So I didn't forget about the successful moon landing that happened recently. I wanted to save it for the end, though. So this is Firefly's Blue Ghost lander. And this is an artist's conception of what it looked like when it was on the moon. And it was also part of the CLIPS program, which I talked about earlier. And it landed softly at Mare Crisium on the near side of the moon in March of 2025. It landed within a 100-meter targeting lift, which is pretty amazing, and used an autonomous hazard avoidance system that had 2 cameras doing navigation, detect craters and boulders. So it was able to do some autonomous maneuvering at the end to make sure it didn't land on a boulder. It operated for a full lunar day, which is 14 Earth days. A full lunar Sunday, let's call it. So, right? Okay. And plus 5 hours into the lunar night. That makes it the longest continuously operating lander to date. It delivered and operated 10 NASA science payloads that all succeeded. And here's a few key achievements of this mission. It had a subsurface temperature probe that drilled about 1 meter below the surface and measured heat flow through the crust. It successfully operated a new instrument called a planet vac, which is a new method of sampling regolith or soil, lunar soil, using compressed gas and very few moving parts. And it demonstrated that it's possible to use Earth orbiting GPS satellites for navigation at the moon. And it also studied how lunar regolith, again, that's lunar soil, sticks to surfaces, and it was able to successfully remove it from a surface using electromagnetic forces. So lunar regolith is going to be a major problem for operating on the moon, and we need to learn to overcome that if we're going to try to operate on the moon in the future. So finally, here's a video put out by the Blue Ghost team of the trip to the moon and the landing. These are actual videos from the spacecraft. That white circle in the background, that's the Earth.
Khan, Chief Engineer on Ops. Y'all select the landing. We're out the moon.
All right, that's the end of my talk, and the next few decades in space are going to be very exciting. Here's some additional resources if you're interested, and I'll be happy to take any questions. Thank you.
That was amazing. Thank you, Ken. Big round of applause, everybody. All right, any questions?
Where's Ken? Where is Ken?
Where are you, Ken?
I'm at home because my wife broke her hand, so she had hand surgery today, and it was very successful. She's rehabbing now, so I'm home with my wife. So.
All right, any Zoom questions from the Zoom members? You can put it in the chat or just ask to unmute. Okay, anybody here? We have one question over here.
Ken, I want to know when they say they're going to make a permanent base, from the first landing to when a permanent structure is there, how long is that process? And do they have designs of what those structures look like? Yeah.
Yes, that's an excellent question. So they do have designs. There's contracts. NASA has contracts out, and the Artemis program. I talked about it more in my previous year's talks, but the Artemis program is designed for other countries to contribute to the effort. So it's not going to be all NASA and all U.S. taxpayers doing it. And so there's, I think, at least 40 plus countries that have signed on to the Artemis program. And I know for one thing in particular, the Japanese space agency is contributing a rover, a pressurized rover that can be used by the astronauts on the moon. So other countries are going to be pitching in. I think until we can actually, it's like a lot of things. Until you actually get there, people are going to be wondering whether it's going to happen or not. But from everything I can tell, there's a new space race to the South Pole, because that's where everyone thinks there's ice underground. If you have ice, you can make oxygen and water and rocket fuel. So that's the most valuable real estate on the moon. So that's why everyone's targeting the South Pole. So there are designs and contracts being let for doing that. It's most likely, you saw that SpaceX rocket, right? It's a very large rocket, and the first habitats are going to be on the rockets that land on the moon. The habitat will be in the rocket. Eventually, will be building habitats and landing more specialized modules. But to start with, they can just live in the rockets that land, there'll be a rocket that lands the astronauts, but there'll be another rocket that lands that's empty, that just has a habitat in it, right? So that'd be the idea.
All right, one more.
How long after the moon effort are they talking about Mars and permanent humans there?
Well, Elon Musk is, love him or hate him, he has a vision to put people on Mars, and the whole purpose of his company, SpaceX, is to put people on Mars. And right now, they're making a lot of money with Starlink and other things and NASA contracts, but they're pushing to put people on Mars. So they're actually going to be sending rockets to Mars. Probably not the next launch window, but the launch window after that. They're going to start sending multiple rockets to Mars every launch window. And they just signed a contract with Italy to send payloads, scientific payloads, to Mars on their rockets. And so what I always tell people at Star Party, especially kids, I say, someone alive today will be the first person to walk on Mars, and it could be you. And so I think by the end of the 2030s, someone will have visited Mars by the end of the 2030s, is my guess.
All right, thank you, Ken. We're going to take a quick 5-10 minute break. Thanks.
All right, thank you.
Amazing. Okay, so it's time for the main speaker. We have Martin Sirk here. He works as a researcher at UC Berkeley's Space Science Laboratory, an alumnus of UC Santa Cruz. He has worked on the Hubble Space Telescope, the Extreme Ultraviolet Explorer, and half a dozen other NASA missions. He is currently working on the Keck Planet Finder spectrometer, and can you help me with this pronunciation? Carruthers Geocoronal Imager. Martin took up amateur astronomy in high school and built his first telescope at age 15, like everybody else. He has been teaching the course Practical Observational Astronomy in the Sierra Nevada since 2000, and has been praised as being able to explain complex scientific concepts in clear, easy to understand language. You are definitely giving the right lecture tonight. He is an amateur naturalist, and he has made hundreds of forays into the Sierras in all seasons. So please welcome Martin. He's going to give a lecture on black holes, dark matter, and dark energy.
There's a former colleague of mine right here. So if I we used to go on picnics together, and her purse was stolen out of her car, and 2 months later a hiker found it in a gully and she got all her good papers back, so she lucked out. No, this was in Berkeley. Yeah. There's in San Anselmo, there's a bear, but I've never heard one in Berkeley. I'm going to be retiring next year, and I hope not. And because of that, it kind of made me reflect on what has changed during my lifetime in astronomy. And so I'm not really going to be telling you everything about black holes because there's way, way, way too much for a short talk. And even less about dark matter and dark energy because we still do not know what it is. But there have been some major advances over the last 45 years of my career. When I was in high school, black holes were still highly theoretical. No one had really strong evidence for a black hole. But they seem to be real. And they're not just real, they're invoked to explain just about everything. Plate tectonics had the same effect on geology in the 60s, is it was considered to be not real or just hogwash, and then suddenly it was used to explain everything. What we call dark matter today, when I was a kid, was called the missing mass problem. And even as recently as 20, 25 years ago, a friend of mine, he did an unofficial poll of just friends, professional astronomers. And he asked them, well, what do you think dark matter or missing matter will be? And almost everyone said, well, it's just ordinary matter, we just haven't found it yet. Well, that's completely changed. Astronomers have been looking for it for 70 years, and they have not figured out what it is. But they believe it is real stuff. They just don't know what it is. So that's a huge change, going from missing matter, which doesn't sound that sexy, to dark matter. If you write a grant to get money and you say, we don't know anything about what we're talking about, we don't know what it is, so give us money. But if you give it a sexy name, dark energy or dark matter, or the missing mass problem, or something like that, then it sounds much more interesting. So galaxy evolution, that's another thing that has changed. I was having dinner with a friend in Santa Cruz about 25 years ago, and everyone I was with were astronomers from Space Telescope, really smart people. And I just said, well, what's driving you to continue doing astronomy? And they said, galaxy evolution. They were really curious about how galaxies change with time. And that was still totally mysterious 25 years ago. H sub naught, that's the Hubble constant, named after Edwin Hubble, who discovered the expansion of the universe in the 1930s. And all that number is, it's the rate of expansion. And when I was at Space Telescope in the 80s, Alan Sandage, who was Hubble's one and only graduate student, gave a talk. And he was older than I am now, so he was at the end of his career. And the astronomers still hadn't figured out what that rate was. And Sandage was in one camp. I can't remember which camp he was in, but there were two numbers that astronomers were throwing out as the rate. One was 50, and the other plus or minus 5, and the other was 100 plus or minus 10. Now those two numbers, those errors don't overlap. They're different groups using different ideas, different techniques, and they were coming up with different numbers, and the errors didn't overlap. So one of the, it's called a key project for Space Telescope, was rather than having one or two people try and figure out what it is, they would make a consortium of hundreds of astronomers, and they all agreed to share the data. And one of those was to nail down what the heck the Hubble constant was. So Space Telescope spent about 20 years of observing to nail that down. And rather pathetically, the number they got was 70 plus or minus 2. So there was a debate. Was it 50 or was it 100? Well, both sides were wrong. And that is really common in astronomy. So whenever you see some big debate in Scientific American about the out of Africa theory for human evolution, or how did humans spread over the planet, it's always presented as this conflict. And you read the articles like, well, those guys don't know what they're talking about. So just because there's a debate doesn't mean the other side is right. And then I was in Seattle, I forget what year it was, but I think it snowed a lot. And Alex Filipenko, an astronomer at UC Berkeley, he gave a talk on dark energy. I forget what year that was, 2001, 2002 or something. And dark energy is even more mysterious than dark matter. And I'm not going to get into it, but it's one of the things I hope to at least mention. So I do not teach from PowerPoint slides. I really, really dislike PowerPoint. So that's why I'm using Keynote, which is just as bad. What's going on here? Okay. I am an amateur astronomer, like most of you in here. And I got into professional astronomy just because my dorm preceptor says, hey, my boss is looking for a student aide. So I said, okay. And I've been one ever since. But I teach an observational astronomy course in the Sierra Nevada every summer. So see me after this talk if you want any information about that. And this is where we observe up on the Pacific Crest Trail at about 7,500 feet. And this glow back here is Sacramento. And it's 70 miles away from our observing site. So I've only observed from Monte Diablo once. And even though you're not right in the city on the summit of Monte Diablo, you're still surrounded by light pollution. It's everywhere. It's only getting worse. So I'm going to kind of guide you through what a black hole is, and then what its effects are on not so much us as individuals, but our understanding of the universe. There's nothing new about black holes. I think they were indirectly mentioned in the 1700s. And then the first kind of modern description of what a black hole is about 1915, right when Einstein published his theory of relativity. So first, do some real basics here. Right now, the only way humans have thought of how a black hole could possibly form is from a star. If I ever am standing in your way, just shove me aside. Where's that laser pointer, Tara? Did you actually have one?
I plugged it in this morning, so it'll be ready to go, and I left it. I apologize. And while we have a quick interruption, there is a car parked in the upper lot. They're going to close the gate, so it needs to be moved if you want to be able to get home tonight.
So, can anyone tell me what a star is in say, a sentence in 1 comma? That's the power source. But what keeps a star from, say, collapsing into a black hole or blowing up?
Balance between gravity and the fusion process. Producing the energy.
Yeah, you two collectively said it. It's in hydrostatic equilibrium, which is the hoity-toity way of saying the forces that are trying to compress it into a black hole are balanced by the heat of the fusion reaction. And if those things are reasonably well balanced, you can have a star live for a really, really long time, which is probably essential for the formation of life, having a stable source of energy. So our sun is believed to have a core where fusion is happening. This is not quite a scale drawing. This whole thing here is the core of a star. And in reality, it's probably about 1/100th the size of that dot. So what's happening in a star is very, very tiny in the core. As those fusion reactions happen, that's where hydrogen is being converted into helium that releases energy, and that energy works its way out to the photosphere, and then that's what we see when we see the sun. We see the photosphere. Photosphere is about 6,000 degrees Kelvin. The core is about 15 million degrees Kelvin. And when a star is doing that, come on, it's the wrong computer. I see my slideshow on her computer more vividly than on my own. This is the most famous diagram in all of astronomy. And it's not just famous, it's exceedingly important. It was the key to figuring out how stars work. It's called the HR diagram, Hertzsprung-Russell. It was independently discovered around 1902, I think. And all it's showing you is the color on this axis and the brightness on this axis. So red is this way, blue is this way, and bright is up. This is for the globular cluster M55. I won't get into the details, but when stars are burning hydrogen at a uniform rate, they tend to lie along a band here called the main sequence. And the only reason the main sequence exists at all is because the star isn't doing anything other than steadily burning fuel. So as a star ages, it does not move along the HR diagram. Our sun would sit right around here. Quick pop quiz. What color is our sun? What's the best description of its color? Yes! The sun is a white star. It is not yellow. It happens to give out huge amounts of yellow light, but white paper and snow and clouds would not look white if the sun was a yellow star. You guys all get gold stars. No, white stars. So our sun is sitting here, and it's been there for about 5 billion years, and with any luck, it's going to be there another 5 billion years. But eventually, it's going to leave the main sequence and start heading up what's called the giant branch. And what happens is, as it's going up this giant branch, the hydrogen in the core is all gone now. It's helium there. But all these outer layers are shells, just like an onion skin. And in each shell, there'll be fusion of different elements, with the heavier ones fusing in the middle, the core, and the lighter ones fusing out here. So you got helium out here and all, oxygen and nitrogen and carbon and magnesium and stuff like that, these layers. So helium is 4 times as dense as hydrogen, and it's starting to collect in the core of a star. So the core is getting denser. Now eventually, the helium starts to fuse into heavier and heavier and heavier elements, and then you end up with an iron core. And iron, oops, wrong one again. This is straight out of a physics book or astronomy book. This shows you how tightly nuclei are packed together, and or how strongly they are held together. So as hydrogen fuses to helium, the binding energy changes. And each time you go down this diagram, you release energy until you get to iron. Iron is at the very, very bottom. And so when you're fusing, you can go in this direction until you get iron. And then if you fission, like plutonium and uranium, when you break those atoms apart, you also can get energy. But iron is at the bottom of the energy diagram. Once you have iron in a core, that's it. The core cannot produce any more heat. So what happens if your source of thermonuclear fusion shuts off? What happens to the core of the star? Shrinks, right? Now, what happens when you compress something? The temperature goes up. So, completely unlike your barbecue where you light it, it's very hot at first, then all night long the coals burn down and they get colder, colder, colder. The next morning your barbecue is the same temperature as the environment. Stars do the exact opposite thing. When they run out of fuel, they get hotter, which is rather non-intuitive. So eventually, now, when the core gets hotter, there's a huge amount of heat now coming out of the core into the outer layers of the star, which are still lightweight, fluffy hydrogen. So the whole star puffs up. And the outer surface of the star cools down. So not only is the star getting redder, but because the outer layers puff up, it's larger. So it has more surface area to radiate, so it's brighter. So because it's running out of fuel, it gets larger, brighter, and redder, which again is rather bizarre. Now, eventually, this process stops, and then what you have is you have a ball of mostly iron and a bunch of other elements, but a lot of iron, surrounded by an extremely tenuous outer layer. That ball of iron is something like 500,000 degrees hot now. It's extremely hot. It gives off mainly X-rays and ultraviolet light. Now, if you have this very tenuous shell of gas surrounding an extremely hot ultraviolet source, what are those X-rays going to do to the gas? Well, ionize it. But when you ionize a gas, it starts to glow. So you get a shell of glowing gas now it's not glowing because it's hot. It's glowing because it's being excited by ultraviolet light. So you've all seen them. What are those objects that are a nice shell of gas with a little white hot star smack in the middle? Planetary nebula. So what was a red giant way up here somehow works its way all the way down to the white dwarfs, which are way, way, way down here. This seems really fuzzy to me. Is this thing as focused as good as it can get? Yay! You're astronomers. Someone should figure this out and publish. Yeah. Well, do you own a slide projector?
Not anymore. Yeah, I do.
Yeah. Mine, it senses how far away the slide is, and when the heat pops the slide, the focus automatically compensates for it. This, nope. Well, since you moved it, also refocus one more time. Yep, almost. You had it.
No, it's fuzzy again. You gotta strike a happy medium between forward and fuzzy.
I think that slider is just very coarse. Well, it's certainly better than it was. There. Okay, everything I've just said about the core gets denser and hotter, the outer layers expand, you get a planetary nebula. That's will be true for our sun. So stars in this region of the HR diagram and smaller, they'll all become white dwarfs in planetary nebula. But stars that's had a higher mass, this is an extremely old star cluster. When it was young, the giant branch wasn't there, and the main sequence went up there. All of these high mass stars evolved more quickly. They've left the main sequence and have blown up or whatever. So that's what I'm going to talk about now. What happens to a high mass star? The exact same thing happens, except because it's more massive, that iron core gets hotter and hotter and hotter. And eventually, when it's about 100 million degrees, the heat alone starts to rattle the iron atoms apart. And eventually, those iron atoms just become protons, neutrons, and electrons, and they're bouncing around. But a lot of those protons fuse with electrons and become neutrons, and they shoot off what's called an electron neutrino. Now, neutrinos can pass through just about anything. Right now, there's 60 million neutrinos going through your thumbnail every second. Most of those are coming from the sun. But neutrinos can go all the way through the Earth and have a low chance of interacting. Those neutrinos, as soon as they're created, they just leave the star. They can go right through the core and out into space. And when they do that, they take some energy with them. And so For millions of years, it would take something like 1,000,000 years for a photon to get from the core of a star out to the photosphere, because it kept bouncing into something. Neutrinos escape just like that. And in a fraction of a second, the entire core collapses into a ball of neutrons. This happens really, really fast. Astronomers don't know how fast, but like a fraction of a second. We're not talking days or months or years. Just like that, the entire core of the star goes from the size of the Earth down to about the size of a city, about 15 kilometers diameter. Now, all these outer layers are still here. And the hydrogen and helium in the rest of that. There's still a lot of layers left. But now there's nothing in the core. There's no source of heat, and there isn't even space. I mean, that's all there is space. There's no matter. So what happens when you pull the rug out? Yeah. All the outer layers start to just fall towards the center. And eventually, the outer layers meet the outer layers coming from the other side, and you get this massive shock wave. And the shock wave bounces back. I should have brought my super ball demonstration. I don't know if you've ever seen it, but it's 4 super balls stacked, and the 3 upper ones are free to slide on a rod. And you have a big one, medium, small, and very small. And if you drop it about a foot, the top ball will shoot up about 30 feet into the air. So all the momentum from the 3 lower super balls gets pushed into the uppermost one, and it just shoots off. Well, the same thing happens in a star. As the outer layers fall in, and they rebound, and they go out. And that shock wave is extremely hot, and it goes through all of these outer layers and heats them up to the temperature needed for thermonuclear fusion. So instead of fusion happening in the core or in these thin little layers, it's happening everywhere in that whole left ball there simultaneously. So you get the supernova explosion, and for about a month or two, the light from that explosion can outshine the light of an entire galaxy. So if a supernova were to go off in the Andromeda galaxy, it would probably get up to about 3rd magnitude, which is the magnitude of Andromeda. And Andromeda has at least 100 billion stars. So it's giving you the light of 100 billion stars all at once. So that's how supernova occur. It's from the collapse of a star, the core, which makes it really, really hot. The heat rattles the iron apart. Neutrons form, and you have implosion and then rebound in a supernova. So that's how you get a neutron star. So neutron stars are not theoretical, they've been observed. Any rotation that the star had when it was young is now spun up in that core. And if the sun was, 1,000,000 miles in diameter, and now the neutron star is 14 kilometers in diameter, it's spinning really fast. So there's a whole class of objects called millisecond pulsars. They're called millisecond because they spin 1,000 times a second. And this has been observed directly with radio telescopes. The Crab Nebula has a pulsar in it that's spinning. And so they're not theoretical, they're real. So, white dwarfs are what our sun will become. Supernovae are what stars in this region of the HR diagram will come. And then, no one knows yet, but somewhere is the dividing line where it's somewhere between 3 solar masses and 10 solar masses. Once you're above that, then instead of a neutron star, the neutron star will continue collapsing into a black hole. So what is a black hole? What's different between a black hole and a neutron star? So when you drop something, it's accelerated towards the center of the Earth. If you knock it off the table sideways, it still will fall at the same rate, but now it's moving sideways. And if you knock it at 18,000 miles an hour, it will fall towards the Earth, but since the Earth is curved, you can match the curvature of the Earth with the velocity. And you need about, I think it's 18,000 miles to get into low Earth orbit. So every massive object has what's called a treetop orbit. That's the orbit that would just skim the surface if you get rid of the air. For Earth, you have to go about 300 kilometers up, and then you can orbit. And that speed has to do with the density of the object. It's not so much its total mass, but its density. So if you were to make another Earth that was twice the diameter, but the same density, its treetop orbit would have the same period as our normal Earth. So it's the surface gravity that determines the orbital speed, the minimum speed needed to keep from crashing in. Well, a neutron star or a black hole has a mass something like 5 or 10 times that of the sun, but a diameter smaller than, a black hole has a diameter smaller than a neutron star. So its surface, what's it called? Its treetop orbital speed exceeds the speed of light. And nothing can go faster than the speed of light in our universe anyway. And so no particle can come out of a black hole, and even light or radio waves cannot leave a black hole. Once they're in for good. And they're just kind of lost forever. So black holes, as I said, were kind of postulated over 100 years ago. And when I was in high school in the 70s, they were still theoretical, although there were some good candidates for them. So black holes have mass, and their mass is a measurable property. Light and radio waves can't leave a black hole, but the gravity from a black hole, it was already there before the black hole even formed. And I don't see why that doesn't suck in the gravity with it, but it doesn't. So, when I was at Santa Cruz, this woman gave $36 million to Lick Observatory to build a big telescope. But that wasn't enough. And then she died, and her heirs reneged on that offer. So Lick and Caltech formed a deal, and together they built the Keck telescopes, which are in Hawaii now. And one of the most amazing cameras on the Keck is an adaptive optics camera that gets rid of the seeing. You're all familiar with bad seeing, especially here in the Bay Area. I grew up in Fairfax and had really nice weather in the summertime, but the seeing was usually horrible. I had better seeing in the fall and the winter than in the summer, because that fog air comes in and just everything is all around. So this is a before and after image with an infrared camera mounted on the 10-meter telescope, 2.2 microns, that's 4 times longer than red light. And what we're going to be concentrating on is this little square here. But here, in this blow-up of the core of the galaxy here, you see maybe 2 or 3 stars. And then here, there are about a dozen. Well, Andrea Getz at UCLA and her team, they've been taking photos of the core of our galaxy for about 20 years now with this camera. So just watch this for a second or two, and then I'll point out some fun things. This is a orbital model fits to their data. So by looking at the images, they can figure out, even when 2 stars are blended, they can figure out where their centroids are and separate them and fit the models to it. So this is 1/10 of an arcsecond. Now, so this yellow star, SO2, just watch its orbit. In 15 years, it has completed 1 orbit around something. Now look at this green star here. It's going to start right there, so watch it. There it goes. And the way it whips around, you can tell that it's not in a circular orbit, it's an elliptical orbit. And you can, by studying all these stars simultaneously, you can figure out not just how fast they're going, but you can actually get the tilt of their orbits as well. And from that, you can calculate the mass of whatever these stars are orbiting. So I'm going to back up here. Way off in the corner here, I should have made it bigger, but it's Kepler's law. Kepler discovered this law of planetary motion empirically using the data of Tycho Brahe. And he noticed that the period squared of a planet in its orbit around the sun was proportional to its radius cubed. And Isaac Newton comes along and he first invents calculus, but he derives that very equation just by considering central force motion and using calculus. So this law was discovered empirically and then derived theoretically. And when it was used to measure the mass of Jupiter using the little satellites that go around, it's really easy to measure their period. You just look in the telescope each night and count how many days. Getting the distance to Jupiter, you can do that on graph paper, at least in terms of Earth distance, the astronomical unit. So Jupiter turns out to have a mass about 1,000th that of the Sun. And then the Earth is about 1,000th that of Jupiter. So Kepler's law works. And if it didn't, a modern astrophysics would be, I don't think there would be modern astrophysics. It's probably the most important law in all of astronomy. And when you apply it to this movie you're seeing here, you get a mass for this thing, whatever this thing here is, which is invisible at these wavelengths, of 4 million suns. So whatever's in the center of our galaxy has a mass of 4 million suns. And whatever it's orbiting can't be any much bigger than that green hairpin turn there. Because if it were bigger, that star would crash right into it. So you can put an upper limit on its size directly from this graph here. So this is, freshman high school math. You can calculate the size, the upper limit, and the mass of whatever's in the center of our galaxy. And you can't see it. It doesn't show up in you can go to longer and longer infrared wavelengths, and there is nothing visible at the center of our galaxy. So whatever it is, it's big and heavy and black. So this is the most convincing evidence of a black hole there is so far. So I'm not going to get into this. Okay. What would happen to us or to the Earth if the sun were to just spontaneously turn into a black hole, like right now? Well, it won't get dark for another, 10 hours, right? So we wouldn't even know that it got dark. But would we feel anything?
It's the same mass, right?
Same mass. Nothing. Maybe the gravity wave detectors would detect a little ripple, a little hiccup, a little burp. But the Earth would continue to orbit the sun, the now black hole sun, indefinitely. Mercury too. The gravity of a black hole is just ordinary gravity. There's nothing different about black hole gravity. It's only when you get down to that last few kilometers do the really weird things happening. And there you can get orbits that decay and change. But those stars that were orbiting in that last movie I showed you, they're going to continue doing that for millions and millions of years. Although it's kind of crowded there, eventually the stars themselves might change each other's orbits. They'll interact. So anything you ever saw in a Disney movie or whatever is a bunch of crap. So black holes have mass, and they rotate, and you can figure out what that rotation is by observing their effects on things that are outside the black hole. But once something falls into a black hole, it's gone forever. You can no longer communicate with it in any way. So other properties that black holes have is if a black hole is spinning, you can get objects that orbit them, and they can kind of exchange energy in such a way that one of the objects falls into the black hole and the other one moves away from it. And the one that moves away from it can actually gain energy. So spinning black holes can energize the regions around them. And that seems to be extremely important in what's going on in quasars and what are called active galactic nuclei. Let me just show you another image here. Now I'm in trouble. Here we go. There's something different about being here than at home, of course. Yeah. I don't understand what's going on. There we go. Okay. I'm sure most of you have looked at M87 in the Virgo. M87 is a bizarre galaxy. I read just a couple hours ago, it has 15,000 globulars. Milky Way has 150, and Andromeda has something like 400, I think. So something really strange is going on with M87. It's spherical. And so where do all those globulars come from? They almost certainly came from mergers. And there's probably 100 galaxies that went into making up M87. And it's also physically near the center of the Virgo cluster. So it's a bit of an oddball. Yet many galaxy clusters have an M87-like object in their cores. Well, it turns out there's a supermassive black hole in the core of M87, and this jet coming out of it is a big radio lobe. You can see it in radio wavelengths, but it's also bright in X-rays. So it's an extremely large feature and very, very energetic. But the only way astronomers can come up with any idea of what's going on here is if you have a spinning black hole that is whipping up magnetic fields and then ejecting things out the poles. Not along the equator of a black hole, but the poles. And there are other jets that have been discovered. You can see them going in opposite directions. So there's lots of evidence for these jets. And it seems like quasars and active galactic nuclei, that's what's going on, because they're incredibly bright at really, really far distances. I mean, that's why we can see them at all. So at some point in the formation of M87 and many, many, many other galaxies, a black hole formed in the core. And it has consequences on galactic evolution. So just like the HR diagram was the key to deciphering how stars work, Sandy Faber, one of my teachers at Santa Cruz, she spent the last 40 years of her life trying to do the equivalent HR diagram for galaxies with some partial success. And it's not as cut and dried, but there's something about black holes that regulates the rate at which stars form in galaxies. And the bigger the black hole, the more vigorous the star formation. And the more vigorous the star formation, the chances of it consuming its gas early goes up, which means there's no new star formation, which means the galaxy turns red as all the blue stars turn into supernovas and disappear. There's no new stars forming that are blue. And so you do get a color shift as a function of star formation rate. And that's a big deal. That's happened in the last 25 years. Is astronomers have a better idea of how galaxies change with time. And mergers seem to be a big, big part of that. And the more massive a black hole is, it might be more disruptive in a merger. And the more disruptive it is, the more chance there is of mixing of gas, which triggers star formation. So it took her entire adult career to figure that out. All right, that's all I'm going to say on black holes for now. So let's pause for some questions now, and then I'll go on to dark matter.
Any questions?
Do you?
She's coming in, Mike.
Yes, she is.
Yeah. If light and particles of matter can't escape from a black hole, what does a jet consist of?
It's ordinary matter that has been accelerated by magnetic fields to near speed light. So it's just hydrogen mainly, just ordinary gas. But it's being directed in a very specific direction, north and south from the pole of the black hole.
Along the axis of its rotation?
Yes. Yes.
So,
Yes.
You said that the stars, when they get denser and hotter, black holes absorb matter. They also have some, they're saying they can't evaporate, but I'm wondering what happens to them eventually, and they just get so much energy they explode, or what's the end?
Well, Roger Penrose and Stephen Hawking and Archibald Wheeler have been asking these questions for 50 years. And from what I've been able to gather, and I'll refer you to this book here. This is a very short introduction series. I own 4 of these. There's hundreds of these books now. These are wonderful books because they're well written and they're edited. And my talk has some recommended reading. It seems like the smaller a black hole is, the faster it can evaporate. What do I mean by evaporate? I haven't even got into that. But Hawking was the one who came up with this, Stephen Hawking. There's a quantum mechanical thing called pair production. And it's a way of, it's sort of like borrowing money without credit and then giving it back before the police catch you. You can spontaneously create particles out of absolutely nothing, but you can only do it for an extremely short amount of time, which has to do with the Heisenberg uncertainty principle. So right next to a black hole, you can spontaneously, out of nothing, create an electron and an anti-electron. And if one of them falls into the black hole, the other one can escape. And so once it escapes, now you really do have something. You don't just have a check that promises you money, you actually have a gold coin now. You got a real electron. So where did that electron come from? It was supposed to come out of nothing and then go back to nothing before the police caught it. But if one of them goes in the black hole, it is lost forever, but the other one can escape now. Where did that come from? And the only answer, it comes from the mass of the black hole itself. So if you do this enough, the black hole loses all its mass and it'll just disappear. I mean, do I believe that? No. But there are a lot of astronomers who take this really, really seriously. So let me continue here. You want to be totally done by 9:15, right? Okay. I will continue answering questions. The bigger a black hole is, the slower that evaporation occurs. So it seems like supermassive black holes will be around forever because their evaporation rate is incredibly slow. Also, the temperature of a black hole is not the 100 million degrees of the core of the star. The surface of a black hole, its temperature is about 1/1000th of a Kelvin. And so it should be radiating photons, but they're so faint that they haven't been discovered yet. They've only been postulated. So it's not true that black holes are invisible, but we haven't figured out how to see them directly yet. I hope, let me back up one. You all saw this in the papers a couple of years ago. You know, the first, quote, picture of a black hole. You're not looking at the black hole. What you're looking at is a region just outside the event horizon where the temperatures are really, really hot because the gas that is swirling into it, the gas does smack into its neighbors and the temperatures go up to 10 million degrees Kelvin. So you get X-rays there. Now, when a photon leaves a black hole, it starts out as an X-ray, but as it climbs out of the nearly bottomless pit to get out of the gravitational well, it gets stretched. So by the time it's far away from the black hole, it's no longer an X-ray, it's a radio wave. It gets redshifted from the X-rays all the way into the infrared, and then from there into the radio. So what the astronomers did, they said, well, if we tune our radio telescopes, we can image just the X-rays that were this many kilometers outside of the black hole. So by fine-tuning the radio telescope, they could select which layer they were looking at. And so what you're seeing here are X-rays coming from just outside the black hole. And as they're climbing out of the black hole, they're orbiting it, and they have just barely enough oomph to leave. So they're actually coming from the side here, going behind the black hole, and then coming out as those radio waves there that you see. So it's a very complicated experiment. And I forget what the angular size is there, but this is the core of M87. So it's something like 100th of an arc second.
So if you were to increase the frequency of the observation there, the black area in the middle would continue to get smaller.
I believe so, yeah.
Till it became infinitely small.
I believe so, yeah. Not infinitely small. The event horizon has a radius, and I think for M87 it's something like 1,000 kilometers. If the sun were to become a black hole, it would have a radius of, I think, 3 kilometers. And if the Earth were to become a black hole, it would be no bigger than a marble. Yeah, kind of mind-boggling. So more questions?
I have an online question.
Yes.
Ken asks, if dark matter is 5 times known matter and we see its effects on a galaxy level, why don't we see its effects on a solar system level?
That question is one I've had a similar one. It's if the universe is expanding, is our solar system expanding, or is, say, the radius of an electron orbiting a hydrogen atom, is that also expanding? The answer for the expansion question is in the presence of matter, the expansion of the universe is not detectable. You can only detect the expansion of the universe far away. So it's in between galaxies. So there's a similar answer for dark matter, is it seems to be just everywhere, very, very uniform. So it is affecting our solar system right now, but at a level so tiny, and it's affecting everything the same way. So it's not pulling Mercury one way and pushing the Earth another way. It's just the whole solar system is sitting in a sea of dark matter. And our whole galaxy is sitting in a sea of dark matter. So here is the evidence for dark matter. It was first proposed by Fritz Zwicky at Caltech in the 1930s. He noticed that galaxy clusters, they were buzzing around way too fast. So either the galaxy clusters were being blown apart, or they were orbiting something 10 times more massive than the sum of all the galaxies. So our Milky Way is doing that, and here I forget which cluster this is, or which galaxy it is. But if you count all the stars here, you can estimate the mass, and you can get a mass distribution. Based on that, using Kepler's law, you would predict this velocity as you move in radius away from the core of the galaxy. So the stars orbiting should have these velocities here. As you go farther and farther and farther out from the galaxy, the stars slow down, just like Pluto goes around really, really slowly around the sun. Well, this is what you predict using Kepler's law, and this is what you observe when you actually measure the velocity of the stars. And Vera Rubin in the 60s, she and her colleagues studied this, and I forget what year it is around 1972, an American group and an Estonian group, they simultaneously published papers that at first they were thought crazy, but within 2 years, everyone jumped on the dark matter or the missing matter wagon. And it went from crackpot theory to an observationally supported fact. But what the heck is it? So, question?
Well, I've seen that. I'm familiar with that diagram because I used it in a What's Up last month about Vera Rubin.
Mm-hmm.
She looked at it at what I called a micro level within a galaxy, but Fritz Zwicky back in the 30s did it in a galactic cluster level, macro level. And he saw the same thing going on with whatever the galaxies were orbiting around. They were going much too fast.
Correct.
Okay.
What's your question?
I'm sorry, I guess that wasn't a question. I'm just pointing out that that was familiar to me, and I realized that you're talking about something I had just recently studied.
You had a question way back there?
Yes. With the 4 universal forces that we know of, gravity, electromagnetism, weak nuclear, and strong nuclear, is dark energy and the expansion of the universe yet being categorized as a 5th universal force?
Not so much as a 5th force, because we don't understand what they are yet. So one idea for dark matter is a yet undiscovered particle that doesn't interact strongly with ordinary matter. But once it does interact, once we discover it, and then based on that interaction, it either will or won't be one of those forces. But right now, we don't know. So let me go with my last slide. And this paper came out, I forget, about 10 years ago. And it's one of the most amazing bits of astronomical research I've ever come across. And I could actually read the paper and understand a little bit of it. This is an image of two galaxy clusters. There's a large cluster here and a somewhat smaller cluster here. So all the white and orange dots, those are galaxies taken from the Hubble telescope. So it's an ordinary visual light image. Superimposed on it is the Chandra X-ray images of this cluster. And the blue light are cool X-rays, and the red light there is hotter X-rays. So what's going on here is these two galaxy clusters collided. And so this one is moving this one, and that one's moving that way relative to each other. Now, the stars in a galaxy collision don't really interact very much. I mean, if this is the sun, a grapefruit-sized sun, where is the next closest star to the sun? How far away it is?
4 light years.
No. The scale model. If you were to make a scale model in this park, and this was the sun, the next star, San Francisco, any other guesses?
Not on the Earth.
It's kind of in between, about 2,000 miles away. Chicago or Hawaii. So if you make a map of the United States, you could fit about 5 suns on it. And the chances of those two bumping into each other is pretty low. So when galaxies collide, the stars don't interact. Gravitationally, they'll interact, and they might disrupt the shape of the galaxy, but the stars themselves don't crash into each other. Nothing happens to the stars. Gas, however, completely different story. The gas does smack into each other. And that's what this red emission is here. This is where the gas from these it's the intergalactic gas in these two clusters collided. And this is the actual shock wave of that collision here. And the gas got partially left behind, because this gas used to be centered here, and this gas used to be centered here, but because they went through each other, the gas got partially left behind. So that's telling you that the ordinary matter interacted with itself, the gas clouds. The stars went right through each other. What you can't see on here is there are hundreds of teeny little blue, they look like little parentheses. There's a whole bunch of them around here. There's a whole bunch of them around here. They're very hard to see. You need to look at the original data. What those little lines are, they're images of gravitationally lensed distant galaxies that are behind the cluster. And based on their orientation and how much warping they are, you can calculate what the mass of these clusters has to be to produce that lensing. The mass of these two clusters is 10 times greater than the sum of all the stars you can see. So this is really, really strong evidence for dark matter. Now, the dark matter, the lensing is concentric with the center of these clusters. So the dark matter passed through without interacting. So dark matter does not interact with itself, nor does it interact with gas. So this is I mean, the Space Telescope is an amazing instrument, so is the Chandra X-ray telescope. But it's understandable. You don't have to be a particle physicist to appreciate the simplicity of this experiment. It's evidence that dark matter exists, and it doesn't interact with ordinary matter, and it doesn't interact with itself. So,
you just expect something similar in the case of two galaxies colliding?
oh, absolutely. Yeah, yeah. So
Dark matter is 10 times regular matter?
that's what it seems like. Yeah. So I lied when I said this is my very, very last. What are we doing on time here? Okay. I'll be completely done in 4 minutes, but I do want to take more questions. For the last 70 years, astronomers have been bickering over this diagram. It's really easy to understand. This is time here, and this is size of the universe. So the three models from Einstein time on were a closed universe, which means it would get bigger, 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 slow down, stop, and then shrink and go back to the big crunch. There was the critical model that said it's expanding. Hubble showed us it's expanding. And it'll expand forever, but at an ever slower rate. And then there was the coasting one where it expands forever at a constant rate. So for most of my career and 30, 40 years prior to that, astronomers have been bickering over these three models. Well, with the supernovas discovered and their distances calculated very, very carefully, these supernovae here, they seem to show that the universe is accelerating. So the expansion is growing faster as a function of time. That was completely unexpected. The astronomers who figured this out got the Nobel Prize. So the only way you can get an accelerating universe is if gravity doesn't quite behave the way we think it does. And there's just that one constant in Einstein's equation called the cosmological constant. If you give it a positive value, then you get this curve here. So there's something about space that when you're far away from matter, space expands. Likewise, gravity seems to not quite obey the 1/r² rule. So there's something really strange about space. When you're far away from matter, space seems to be different than here in this room. So no more talking from me, but any more questions?
More about dark matter, but I wondered if anyone's ever talked about the idea that maybe the matter isn't, that dark matter isn't a point-like particle. I know it sounds kind of crazy, but you know about Bose-Einstein condensates and superfluids. Maybe there's something like that, so that's why we can't detect it, because it's not a point-like particle. It's, I don't know. I'm just wondering if you've ever heard of anything like that.
This is not my field. I don't study this stuff. It's way too complicated.
Yeah, I'm sorry.
I can't even speculate. Most physicists think dark matter is some kind of particle.
Yeah.
At one time I thought it was neutrinos. But neutrinos have been shown to have finite mass, but it's not enough. It just doesn't add up.
I'm not saying it would be exactly like a superfluid, but maybe we have those properties. I don't know.
Not my field. I studied particle physics 45 years ago in college, and it seemed totally confusing back then. There were 200 particles known 45 years ago. Now there are a handful more.
Can you say they even exist? I mean, if you believe in
No.
Copenhagen interpretation.
Mesons and neutrinos and tau particles, they all exist. They've been shown in bubble chambers to exist. But there's an experiment that was running for the last 2 years in South Dakota, in the mine, looking for dark matter particles. And after 6 months runs, 0, 0, 0, 0, they just didn't find anything. So we still don't know what it is.
Thank you.
Let me not pontificate, but if anyone is interested in black holes, I highly recommend the short introduction. If you're interested in relativity and what's going on near the surface of a black hole, this book by Lewis Carroll Epstein in San Francisco, it's really, really good. It's about the only popular book I've ever read on relativity that made any sense whatsoever. Yeah. And then I have 2 textbooks here too that are both excellent. This one is written for the physics student, but it's still readable to the layperson, done by Frank Hsu, Berkeley. He's retired now. And this is what's used in college classes today for freshmen, and it's also a fairly good book. So I'll leave these out here. You can look at them. And if you publish, I can convert this keynote to PowerPoint, send it to you. You can publish this last page in your newsletter. But these are the 4 books that I just mentioned.
All right, thank you so much.
All right, thank you.
Like black holes and how it gets down instead of X number of kilometers. When you go to that singularity in the whole universe going back.
That's what the singularity means. The Schwarzschild radius is not the same as the singularity. Schwarzschild radius, that's where the escape velocity equals the speed of light. So that's kind of the boundary of inside and outside the black hole. The singularity is further in. And there, our laws of physics just no longer work there. So we don't know what's going on inside the black hole. It probably would never come out. Yeah, because it has mass. Well, it can't get out. Right, suppose the gravity. It's not stopped, but it can't escape. Thank you. It's gravity. Right. Which implies that the mass of larger things than what you see. Gravity. Oh yeah, yeah. It obeys gravity, but it doesn't bump into gas. Oh, you lost one. What Einstein says is when you're far away from matter, all clocks run at the same speed. As you get closer and closer to a massive object, clocks slow down relative to the ones far away. So what you're saying is maybe even the ones far away, when they're really far away from matter, they might be like, that's argument. Yeah, I don't know. Once matter goes in, it doesn't matter what it was. Now the black hole is matter. You cannot tell what that matter was.
But I was there working as my work experience had been software engineering. And so at the time for that project, I was
Yeah, they're inexpensive, like $10 new and $4 about you.
A programmer, and then later I became, it's just like, I was there for a few years.
Oh yeah, I don't have anything here.
The satellite, on his computer. Yeah. And it was, he got to come. They got to come. I mean, normally they would, but family and friends got to be there, not at the launch, but yeah, I worked on that for a couple of years, and then I took and then first, and then about 6 months old, I went back on and off of part-time.
Yeah, that's we're just above CRC.
Oh, okay. How satellites are. They keep going, you know. That's what I mean.
It's this Sierra Nevada Field
So it
Campus.
was like 10 years
To
old.
SSD.
Yeah.
Oh, nice.
Yeah.
Okay, cool.
Well, that's the one
And it
from
kept
past.
me funny, and finally they said, we're done. And so we had
1 mile east of Bassett.
Yeah, they,
Yeah.
that's it. It was it.
Yeah.
They let it through.
Bassett's
They
just
allowed it
a
to
little
run.
hotel and a store.
Basically.
Yes, that's nice.
Yeah, well, it was done, but it lasted a
I
long
went to
time.
a weekend event up in here in Nevada.
Yeah, we're still working.
It was kind of on, it was on the Nevada
No,
side,
I didn't go back.
at Lake Tahoe.
As
It was a private ranch. And we had a astronomer who actually, no, I'm sorry, he gave a lecture, and then we were invited to go up there to this ranch. They had a Celestron C-22.
Wow.
Yeah. And we brought it up into teams, and the
But I always imagined,
our leader gave us some problems to solve on paper, and then go up and get it.
Yeah, I've observed from Tahoe. It's fairly dark there.
Yeah. Yeah. This is really dark up in kind of the northeast corner. Yeah, that's quite a
but anyway, I thought when my kids
and your granddaughter there.
connect with my own
Yeah. Yeah, I enjoyed it. I started working at Lake Observatory when I was in my junior year.
Wow.
And I worked there about 2.5 years.
that I had worked part-time on projects.
So yeah, by the time I left, doing research similar to what incoming graduate students would do.
What, if anything, can you say about Neil deGrasse Tyson's relativity to people in a hurry? Have you read that?
No, I haven't read that one.
And I still have today.
He's a good speaker, so
yeah.
he probably makes it easy.
Getting to that age, and all my
But
friends say.
but this book is definitely a good one.
Louis Carroll Epstein.
Just wasn't time, but I still, I mean, I'm still interested. It's like I still read,
Yeah, there are about 50 courses there
but
every
I'm not
summer.
that interested.
Bats,
Observing when I try and
birds,
observe.
insects, geology.
illustrator why I couldn't get my eyes focused. And it was explainable, but I was so discouraged. So I'm just not.
It depends on the course. My course
I get it.
is 5 days, 5 minutes.
I'm gonna ask him for is there, does it start already? Should I take a picture of this?
You want to hear?
What?
What are they talking?
Is that it?
The Sierra thing, yeah.
Huh? Yeah. Thank you. Okay.
All right.
So your project in the Sierra is just astronomy, or you have other projects?
Oh, no, there are 50 different classes taught there, which is different.
But yours is just the astronomy.
They wrote you in there.
Yeah.
Yeah, that looks interesting.
I love little books like that.
Yeah.
Well, no, that was a great talk. That was amazing.
Oh, good. I'm glad it went over well.
So that last question the guy said about, what if dark matter is it a particle? And I'm thinking,
How many years has it
maybe
been
he
here
means is it a field or a fluid?
Right.
But when you were talking about how those two galaxy clusters passed through each other and they didn't interact, that kind of makes me think it's more likely a particle and not a field or fluid, because then they would interact. That's what I think.
I don't know.
Well, that was the